Hi, my name is Sharon Acoff-Sledge, and this is my presentation on geometric thinking and understanding for CME 730, Alabama A&M University, Dr. Kimberly Burton. I teach accelerated sixth grade math, and I teach regular eighth grade math, which is an inclusion class. So I'm going to be coming from two different perspectives as I reflect on the two articles that I read. Now, I read Interpreting Student Understanding in Geometry, a synthesis of two models by John Pegg and Jeff Davey, and an analysis of the essential understandings in elementary geometry and a comparison to the Common Core standards with teaching implications by Crumpton and Ferguson. Now, both sets of authors offer valuable insights into teaching and learning of geometry, and I believe they align well with classroom instructional needs, but they could be fine-tuned based on just individual classroom experience. I chose these articles because I did see a lot of implications for my current classroom environment, especially with teaching the two different types of classes. And I'm going to give my thoughts about the two articles I chose and my recommendations for any modifications that would make their concepts fit better in my classroom and in future classroom, my current classroom and in future classrooms. So Pegg and Davey, in their paper, the synthesis of two models. This is actually part of a book, which I'm going to get. But this focuses on interpreting student understanding in geometry through progressive stages of thinking. So the strength of their perspective is how it's structured. It provides a clear developmental framework for understanding how students progress in their geometric reasoning. So as they develop through different stages, their geometric reasoning should align with those stages. They emphasize the gradual development from visual to more abstract concepts. So according to their theories, by the time a child is in high school, they should be able to think more abstractly about geometric concepts, although through elementary and middle school, we may not have relied as much on abstract concepts, but rather visual models. It is our goal to progress them from visual to beginning to think abstract. And with my accelerated class, I do have to do a little bit more of that. So connection to the classroom, the observation that students' geometric thinking evolves over time and through interaction with increasingly complex tasks is spot on. And I put since I teach, but since I teach accelerated and regular, that progression looks different because I have students with different needs. I can see their understanding shift. Last year I taught all regular, but I could see their understanding shift from concrete representations to more formal geometric properties because I have that benefit of teaching them in sixth grade and in eighth grade. But one example is in my accelerated sixth grade class, we will explore the area of polygons. And I've observed that my students will begin by relying heavily on diagrams and physical models coming out of elementary school. However, over time, they begin to conceptualize these things, these shapes, geometric shapes, more abstractly. Whereas in elementary school, they may have memorized formulas. When we get in sixth grade, we'll talk about perimeter. It's like walking around a figure. So they begin to more abstractly see, and rather than memorizing 2L plus 2W, 2 times the length plus 2 times the width, they begin to understand why it's that because they can visualize walking around a building. And so this aligns well with their stages. And just reading their article on the developmental approaches and how their geometric thinking progresses, this is going to allow me to scaffold my lessons better and ensure that they're ready to move on to the next level. So they could go from the area of a 2D figure to the area of a 3D figure pretty easily. Now, Crumpton and Ferguson, they compared the essential understandings and common core standards. And their main criticism is that standard curriculum doesn't adequately represent deep geometric thought. They think it's too surface. And I agree to some concept, because like in eighth grade, we learn Pythagorean theorem. And if a child does not have a concept of right triangles without a visual model, they would have problems. They will have difficulty with the Pythagorean theorem. And sometimes we have to remediate that learning to get them to visualize what is the hypotenuse, and the hypotenuse is opposite the right angle. If they don't have those concepts already down, they have a difficult time with the Pythagorean theorem and the converse of the Pythagorean theorem. Um, and so they say the standard curriculum doesn't represent it doesn't really develop foundational thinking. And to some, I agree. Uh, they critique, they say common course coverage of geometry is sometimes too narrowly focused on procedural knowledge rather than conceptual understanding. And I think that's valid, especially since we have our standardized test that we do once a year, ACAP, where schools are ranked. So we sometimes will default to teaching the formula and memorization of the formula, especially when we begin to run out of time with our lessons and that test is coming up. I've seen students who can mechanically apply the Pythagorean theorem, but they can't explain why it works. So we do need to get, and I recently read an article where two girls, I think in middle school, were able to prove it to some extent. And I've got to get that article and read more on that. But I think those girls have really had a conceptual understanding of the Pythagorean theorem and why it works. So Crumpton and Ferguson say instead of just this approach of memorizing formulas, students need to have geometric reasoning. They need to understand that more so. For example, like when we do the area of polygons, let's start with a rectangle and explain that if we cut it into two pieces, we have two triangles, why that formula is 1/2 the base times the height. Once they begin to see that, why do we sum the bases on a trapezoid? Why do we, and then multiply by the height and take half of that sum of the bases? So we need to know that that's the average of the bases because of how it is reshaped. So just things like that kids need to learn and to develop a conceptual understanding so that they won't just have to memorize formulas. And once they get that conceptual understanding, they won't really need to memorize formulas. They can conceptualize it and know it. Now, for the classroom, I agree with Peg and Davy that there is a progression in geometric thinking, but that's not always a linear process for every student. It's just not. Some students will stay visual longer than others who might be able to jump readily to the abstract. In my accelerated classes, even though my kids are very, very intelligent, some of them would get bored if I stayed on the basics for too long. They need to go on to the abstract, where some of them need to stay on visual models for a while and then move on. So I would modify that by allowing more opportunity for individualized progression, maybe with stations and different things like that, to allow students to move on when they're ready. And Crumpton and Ferguson, I agree that there needs to be foundational knowledge. But again, in my accelerated classes, I found that students often need exposure a little bit earlier. Most of my students, their parents are engineers and things like that. So they need to be, and they've probably already been exposed to some of this, but they need to be exposed to a little bit more advanced topics. And sometimes we need to stay there a little longer on the foundational knowledge. Whereas with my eighth graders, for some reason, they forget their foundational knowledge. So There has to be a re-emphasis on it before we can move on to more advanced concepts. Both articles are highly applicable to the teaching concept, my teaching context. With Peg and Davy in their stages, that is useful in developing a roadmap to see where my students are in their geometric reasoning and understanding. And it will help to differentiate instruction. Like I said, some can move on, some want to stay on the visual model a little longer, but this will help me to scaffold and move those students up so they can get to the more abstract reasoning. There's just some things in their article that would help me to identify which students who are still at the visual stage and how to move them on. So I could provide them with hands-on models and things like that, whereas others might be ready to go straight to the abstract concepts. I'm gonna and with Crumpton and Ferguson, I felt a little guilty because I do need to do more exploratory tasks, especially when we get to geometry. And this would help students move beyond memorizing formulas, and it would help them to have a deeper conceptual understanding of geometry. I think both articles are helpful. Both articles were useful. I do plan to do more research on those. Um, and I had actually read Peg and Davy's article before, and as I read it again, I began to remember some of the concepts that I had read before, I think in a professional development. So this is my analysis. Thank you.